England at Oxford or one of these places, went to the US for a PhD at Harvard, where he worked with some linear superposition of Sid Coleman and Frank Wilczek, and did postdocs at Santa Barbara, I think, at Cornell, at Princeton, MIT. I actually inherited an office from Mark once. Went back to England, took a job at Glasgow, returned to the US, and took a position at Washington University, where he also spent, I think, almost a decade or a full decade being department chair. Mark, over the last really 20 years by now, I think, has spent a lot of time thinking about transport properties in dense matter and how that affects astrophysical objects like neutron stars, mergers, and the like. And that's also what he will talk about today, which is dynamics and dissipation in neutron star mergers. So the general announcement, if you have a question during the talk, I would ask you to put that in the chat, and I will take a look and somehow try to decide whether that's sufficiently urgent that we should stop Mark. And other than that, we'll try to deal with questions in the end. So thanks a lot, and we're happy to have you, Mark.
Okay. Thank you very much. Thank you for the invitation to talk to this group. It's a pleasure to be here. The work I'm going to talk about, as you just heard, is about neutron star mergers, and it's based on this set of papers from the last few years. And of course, as always, there are more on the way, and is funded, I should say, by some combination of the Department of Energy, and I'm a member of the MUSES collaboration, which is developing software for equations of state in neutron star mergers and heavy ion collisions, and is funded by the NSF. So the outline is that you may have heard talks about neutron stars and neutron star mergers before. They are, as you know, like experiments. They're in some ways like very large astrophysical heavy ion collisions. And although they're not purposely done by humans, unlike heavy ion collisions, we can still try to use them to probe the properties of dense matter. And the sorts of things you'll have heard about if you've been to talks about this is mostly the equation of state. People mostly talk about the equation of state. But for this talk, I'm going to be treating the equation of state as more of a sideshow, something that you may need to know, but is not the central question. And what I'm going to be more interested in is out of equilibrium phenomena. And in the interests of having one thing to talk about, I'm going to talk about flavor equilibration, which is related to bulk viscosity. But one can also, in this context, think about thermal equilibration of this system and its related transport phenomenon of thermal conductivity. And you can talk about the equilibration of shear flows in the system, and that would be related to shear viscosity. And a thing that I want to emphasize about this is that, in general, these sort of transport equilibration type phenomena are better than the equation of state if you're interested in distinguishing different phases of this dense material. Because, as we already know from terrestrial condensed matter physics, different phases can have very similar equations of state. You know, you wouldn't use the equation of state to distinguish a superconducting metal from a metal with regular electrical resistance. You would use transport phenomena. They're much more sensitive. They're sensitive to the low energy degrees of freedom, and that makes them a better probe. So it's worthwhile, I think, to ask about how these things might play a role in neutron star mergers. So the thing, as I said, I'm going to talk about is flavor equilibration, which means getting the proton fraction right. And there are various names for this that will crop up in the talk, and I'll try and make sure that it's clear that they're all pretty much the same as each other. So what I'll be talking about is flavor equilibration, and it's one of its manifestations, bulk viscosity, how that arises, some interesting features of bulk viscosity, like that it's a resonance, and how you might see its effects. One way would be that density oscillations get damped. In terrestrial condensed matter, you might talk about that as sound attenuation. but I'm going to talk about it as a damping time for density oscillations. So here is, of course, the obligatory picture one has to have in one's passport if one wishes to enter the land of talking about hot and dense matter. So you've seen this before. This is kind of a cartoon picture, chemical potential pushing you towards higher density of baryons along the x-axis, temperature along the y-axis. And this version of the picture is focused on which parts of nature probe the different regions. So we have heavy ion collisions probing the higher temperature, moderate density range, distinguishing the quark-gluon plasma from the hadronic phase. Neutron stars tend to be low temperature by QCD standards, pushing up the mu axis here. Isolated neutron stars have cooled off and are quite cold. Neutron star mergers are temporarily warm, you might say, on this scale. And we have various different features. We expect gas-liquid transition for nuclear matter, superconducting and superfluid phases of nuclear matter here at low temperature, and so on. Now, you can then superimpose on this picture some of your guesses about possible phase structure. You're very familiar with this region, the possible critical endpoint here, and the search for that. In neutron stars, one's more interested in the low temperature, high density phases. We expect a phase of quark matter, color flavor locked quark matter up at the very highest densities. We expect nuclear matter down at the lower densities, and who knows what in between. Could be something very complicated, some strongly coupled phase. People talk about various possibilities such as quark-ionic matter. Who knows, right? And neutron star mergers are interesting in that they probe the region where we think some of this interesting stuff might exist. They heat up a neutron star, basically. So that's why we're interested in mergers as this possible probe of an interesting part of the phase diagram. Now, if you want to use mergers, then you have to do some of the same things you have to do with heavy ion collisions, such as have some sort of handle on what physics you think is unfolding during the process. And in the case of mergers, you want to perform simulations that incorporate the correct microscopic physics, play it out through the astrophysical scenario, and lead to some predictions of what we should see from planet Earth. So, for example, there's the gravitational wave signal. Not the only signal, but one of them. So the situation with a merger is you have this pair of neutron stars orbiting around each other, spiraling inwards, radiating gravitational waves, losing angular momentum that way. Finally, they collide into one object, and then they ring down and perhaps collapse into a black hole, perhaps stay as a heavy neutron star. And as I said, one of the things that we might see as a manifestation of this would be this gravitational wave signal, where people have done numerical simulations of two inspiraling objects and calculated a very difficult, very intense numerical calculation using the nonlinear equations of general relativity on dynamically discretized space-time, all very, very challenging. But in the last 15 years, they've managed to do this, and they can predict a gravitational wave signal based on the inputs that they put in, such as the microscopic physics. And the microscopic physics is the part that I'm focusing on. And as you know, there is data on this. The best data is still the first data in this case, the 2017 merger that was observed. And you see here the frequency, it's inspiraling. They're getting closer and closer. The frequency is going up. They're going around each other faster and faster and faster. And this is with LIGO. And somewhat frustratingly, the noise curtain comes down and the signal disappears at the end of the inspiral. You do not actually get data from that final merger into one object at this point. However, we hope that future gravitational wave detectors, which are in the works, will get that part of the signal. They'll get to hear, as you might say, the actual merger itself, where we expect the most interesting phenomena to occur. So for now, one wants to lay the groundwork for that by helping the people running these huge GR simulations by providing them with microscopic physics and helping them to get the microscopic physics right. So this is the context that that those of us who are in that part of the pipeline are thinking about. You've got this merger, these two objects coming together, very high density, very high temperature, densities up to a few times saturation density, like the middle of a neutron star, temperatures, which according to the current simulations can get up to the 80 MeV range, hot for a neutron star, not hot for a heavy ion collision, somewhere in between. And one, as I said, one wants to help the merger simulation community incorporate all the relevant physics in their simulations. So here's an example of how that's being done in the case of equilibrium physics. I'm not going to focus on equilibrium physics in this talk, but here's an example that's out there from Most et al., where they're trying to see gravitational wave signatures in that gravitational wave signal of features of the equation of state, like a very dramatic feature, like a step in the equation of state, a first order phase transition. So here they run their merger simulation for two different equations of state, one purely hadronic, one when they say with quarks, they mean a first order transition density jump to quark matter. And they look and they see a difference between the red and the black. They see different gravitational wave signatures, a different length of the ring down, phase differences in the frequency, and so on. And that's their sort of holy grail. They're looking for signatures of some microscopic physics, in this case, a first order phase transition. So what I'm going to talk about, though, is out of equilibrium, not super far out of equilibrium, you know, baby steps, but out of equilibrium, equilibration properties of dense matter. And what we need to bear in mind is the time scale. So if you go back to this, you see the horizontal axis of the time on which this gravitational wave signal unfolds is on the millisecond time scale. Here we go, 0, 5, 10 milliseconds. So that's how long it takes for these two neutron stars, when they get close enough and touch, to go from two different objects very close to each other to one object that is then sort of smushing together, very dramatic, violent fluid flows, and then ring down. So you're talking about, you know, 5, 10 millisecond time scale. So the point there is that you're interested in equilibration times that are in that range. You're not interested if there's something that takes an hour to equilibrate, then it's basically frozen during a merger. So you're not really interested in it. So what we want to know is, are there things that get driven out of equilibrium but then equilibrate on that 20 millisecond time scale? And if there are, that physics needs to be incorporated into the simulations of the merger. So here's now something that shows you a little bit about what's going on as a function of time. This is density in units of nuclear saturation versus temperature in MeV, 2 milliseconds and 10 milliseconds after the merger in one particular simulation from the Razzola group at Frankfurt. And the idea of this is just to show you that there is indeed quite a lot of scope for out of equilibrium physics. So you see here that at this moment, 2 milliseconds after the merger, they've plotted every point in the merger. Where is it in the density temperature phase diagram? They've color-coded it by how far away it is from what's going to be the middle at the end of the day. So this is the center of the merging region. These are the edges of the merging region going in spectral colors from violet to red. And you see there's quite a bit of range of different temperatures, neighboring regions being at different temperatures. There's temperature gradients. So that means you expect possible thermal conductivity effects. There's fluid flow. You can see that the situation is changing dramatically over time between 2 and 10 milliseconds. The density profile is changing. And so there's fluid flow, and you can guess that some of it might have some shear. And there's time variations in density. Again, you're going from low density to high density. And if there's time variations in density, then as we'll see, that leads to things being driven out of flavor equilibrium, and that can lead to bulk viscosity. And so this last part's going to be the thing that I talk about today. So let's just focus on that for a second. So if there are density oscillations, and I'll show you in just a second that there are, then you expect them to drive you out of flavor equilibrium. And by flavor, I really mean proton fraction, isospin, up and down. That's what we're talking about. And the reason for this is that in any nuclear equation of state, and here's an example of one that I'll be using. It's a very standard one, so I'll use it to illustrate things as we go through the talk. This is that equation of state, and this is telling you the proton fraction, what fraction of the nucleons are protons, as a function of density in units of saturation density. And you see as the density goes up, as you compress your nuclear matter, the proton fraction is going up, starting off at about 4% and rising to something more like 10% over the range of densities that we expect is relevant for neutron star mergers. This is a thing called the Dirac-Diercke threshold that we may or may not end up talking about. And the point is that some combination of equilibration via the weak interactions, which people often call beta equilibrium, so that word will come up again. Beta equilibrium just means the same thing as flavor equilibrium. It just means equilibrating the proton fraction by processes that turn neutrons into protons. So beta equilibrium, electrical neutrality, the nuclear symmetry energy, all these things contribute to exactly what this curve looks like. But every nuclear equation of state has a curve like this that says that the proton fraction is varying, rising as a function of density over this density range. But of course, this change in proton fraction doesn't happen instantaneously. And the question is, what's the time scale on which the system, when you compress it from 1 to 2 times saturation density, say, it quote, wants to change its proton fraction from 5% to 8%, but how quickly can that happen? How quickly can the proton fraction equilibrate? And is that going to be a relevant process happening on the time scale of the merger? So just to show you that there are such density oscillations, this is data from a simulation again, where as a function of time, milliseconds, typically 10, 20 milliseconds, they've tracked various little fluid elements in their merger simulation. So they've selected some fluid elements at the very beginning, and then they've followed their history as they get carried around the place, violently pushed around, and this tracks their density. So a bunch of different fluid elements for the different curves here. And what you see is that these co-moving fluid elements, these tracers, experience some quite violent density oscillations. So they start off, these ones, around twice saturation density, but you see in the early stages, in the first 5 milliseconds or so, during that first going from 2 objects to 1 object moment, they experience violent density oscillations from 2 to 1 to 3, 50%-ish amplitude in density. And after that, they still have density oscillations, but they settle down to a more modest amplitude. And you see that the typical frequency is in the kilohertz range. So milliseconds, again, is the typical time scale here. So you're seeing density oscillations, which can have quite high amplitudes, occurring with roughly kilohertz frequencies on the millisecond time scale. So our question is, okay, we've got these density oscillations. We know that the system is trying to re-equilibrate its flavor, in other words, its proton fraction. Do these oscillations drive the system out of flavor equilibrium? And does the process of re-equilibrating the proton fraction affect the oscillations in turn? So, okay, how is it that flavor equilibrates? How is it that the proton fraction settles down to its correct value for a given density? As you know, there's only one interaction in the standard model that can do this, only one interaction that can change the proton fraction in nuclear matter. That's the weak interaction. And it happens via processes of this kind. Neutron turns to proton plus electron. Of course, there are neutrinos in the game as well. And I'm not showing what they do because, as we'll discuss later on, neutrinos are a bit of a challenge. And their exact way in which they participate can depend on density and temperature and stuff like that. But so what we want to do is calculate the rate of equilibration. How quickly does the proton fraction go back to its long-term value for a given density? Does it happen on the time scale of the merger? If so, that physics ought to be included in simulations. And does that process of relaxing back to the correct proton fraction, relaxing back to flavor equilibrium, does that process lead to any effect on the density oscillations themselves? For example, dissipation, damping via bulk viscosity. So that's what I'll be talking about. I mean, it might be a good moment to, so yeah, so my plan now is to estimate the damping time for density oscillations. How are they damped as proton fraction equilibrates itself via the weak interaction? So since I've set myself a specific question, maybe I'll take a little pause and see if anybody has any questions that they would like to ask.
No, I think we're good for now.
Everything okay? All right, I will press on then. So here's my task. What's the damping time for density oscillations caused by equilibration of the proton fraction? So let's just look at what's going on when we have a density oscillation. So we can think up a generic density oscillation. This part, what I'm going to do here, is true in any context, really. It could be in terrestrial condensed matter physics. It could be in a heavy ion collision. You have a density oscillation with some frequency, angular frequency omega, with some amplitude delta n. N is baryon number for us, and some background density around which you're oscillating. And so you can ask how much energy is carried by this density oscillation, and it's pretty much a harmonic oscillator. You know, its restoring force is something parabolic for small amplitude oscillations, which is the linear response regime that we're going to work in. Nonlinear is interesting too, but you know, one thing at a time. So the energy of this density oscillation, it goes like the amplitude squared, and it goes like the spring constant, and the spring constant for dense matter is the nuclear incompressibility, which is a feature of the equation of state. And these other factors like the background density and this factor of 18 are just to do with how the incompressibility is defined. So that's the energy this oscillation is carrying. The other thing you're interested in is how quickly is energy being sucked out of this oscillation by some sort of dissipation, which in this case would be bulk viscosity. And I will explain later on how you get bulk viscosity from flavor equilibration, from the equilibration of the proton fraction. But for right now, let's just assume there's some bulk viscosity there and ask how quickly it's going to damp this density oscillation. So the definition of bulk viscosity is such that the rate at which this oscillation loses energy goes like the amplitude squared, and it's got these factors of the frequency squared and 2 because of the definition of bulk viscosity, pretty much. So you've got an amount of energy, and you've got a rate at which you're losing energy. So if you want to know how quickly is this oscillation damped, the damping time, you just take how much you have divided by how quickly you're losing it, and that tells you how long it takes for you to lose it. So you divide these. Linear response means that the amplitude cancels out, and you've got a property of your material, depends on the frequency of the oscillation, but it depends on the background density. But roughly speaking, it's what you'd expect. You've got the nuclear incompressibility in the top and the bulk viscosity in the bottom. And that makes sense because if the incompressibility is big, your oscillations store a lot of energy, so it takes a long time for that energy to be taken away by any kind of dissipative process. The more money you have in the bank, the longer it takes you to lose it. On the bottom of this formula, you've got the bulk viscosity. Obviously, if the viscosity is higher, you're losing energy more quickly, and so the damping time gets shorter. So the damping time is, roughly speaking, you know, some measure of how much energy your oscillations carry divided by some measure of how quickly they lose it. And we want to know how big this number is. What is this damping time? And in particular, is it going to be relevant to mergers? Is it going to be on the 20 millisecond time scale? So I'm just going to cut straight to the answer here because you don't want to be led through a long and complicated calculation, at least not until I've told you where you're going to end up. So here is an example of doing that calculation for neutrino transparent matter, which is an approximation, but we can talk more about neutrinos later on. But at least if you assume the matter is neutrino transparent, then you calculate this damping time with some equation of state and with some treatment of those weak interactions that turn neutrons into protons and achieve flavor equilibrium. And you get this set of contours. So this is baryon density along the bottom, 1, 2, 3, 4 times saturation density, temperature up the side here in MeV, 1 to 9 MeV, and you get these contours of how quickly a density oscillation would be damped. And what you see, I'm going to explain the features of this plot. The rest of this talk is in some ways explaining features of this plot. But let's just look at the numbers to start with. So you see that there is indeed, for this particular equation of state, IUF, one of the standard ones, and using the various approximations that we made that I can talk about more if people want to know, you get that there is indeed a region at sort of moderate density and temperatures about in the 4 or 5 MeV range, as I think, here we go. Well, I can pull back from that. There is indeed a region where the damping of sound waves, of density oscillations, is happening on the 25, in this case, millisecond timescale, fast enough that it will be relevant for the violent dynamics of the early stages of the merger. And so this sort of physics ought to be included in the simulation. Now,
Mark, do you have a second? So Huichao has a question. You want to unmute yourself?
Yeah, I just ask whether you estimate only bulk viscosity from density oscillation. Is it related to the compression process or change of volume? Is this the reason you got bulk
yes.
viscosity there? Okay.
Yes, it's so if I go back to here we go. We're looking at a density oscillation of roughly 1 kilohertz frequency, because that's what we see actually happening in the mergers. And we're looking at a density oscillation, some little fluid element that's being compressed at 1 kilohertz. Is that what you're asking?
Yes, thank you. Yeah.
Okay.
So in
And we expect-
principle, I mean, if you have a density oscillation at approximately constant entropy, then you are oscillating in temperature as well.
Ah, okay. So that's getting into so that's where yeah, that's digging beneath the surface of this. So hidden away in this bulk viscosity are various susceptibilities of the material. And what you're pointing out is that you have to decide, are you going to use isothermal or adiabatic susceptibilities depending on the thermal conductivity of the material? Is it thermally equilibrating on the same time scale, or faster or slower? At these temperatures, these temperatures are fairly low by sort of QCD nuclear standards. So there isn't a huge amount of difference between those, it turns out. But yes, you're absolutely right. In general, one would have to, I think this calculation was done with isothermal, and they probably adiabatic is a better approximation, because we think thermal equilibration is slow on this time scale. But that is indeed a valid point. Okay, so let me just talk about a couple of features of this plot. One is that you see, as you go out to higher densities, the damping is getting slower. So roughly speaking, you track out here, you see it goes from at 3 times saturation density, it's in the 50 millisecond time range. 4 times, it's in the 100 millisecond. Out at 5 or 6 times, it's getting out to 1 second. It's taking longer for density oscillations to be damped by bulk viscosity as you go to higher density. And the dominant reason for that is to do with the incompressibility getting bigger. Yes, the bulk viscosity is getting slightly bigger too, but roughly speaking, it's just that the oscillations carry more energy at higher density. The spring constant is higher. It's resisting compression more. So an oscillation carries more energy. So it takes longer for a given amount of bulk viscous damping, but bulk viscous dissipation to take away its energy. So that one is sort of understandable. What's less obvious is the highly non-monotonic temperature dependence. What you see here is, as you go at any given density from low temperature to high temperature, you see this damping time. At low temperature, it's slow. Oscillations are not damped very much. At high temperature, it's slow, high meaning 10 MeV plus in this case. It's slow. Sound oscillations take a long time to damp. But there's a maximal damping region that seems to be typically around 4 or 5 MeV. 3 here is wrong. It should say 4 or 5. Around 4 or 5 MeV temperatures, that's where the damping is fastest, and it's clearly non-monotonic, and that's what I'm going to talk about now, because that's an interesting feature of this flavor equilibration bulk viscosity physics. So what I want to do now is try and understand, why is it that as you turn the temperature up, at first there isn't much damping of density oscillations, then there's a lot, and then there isn't much again. So this gets us to thinking about what's bulk viscosity. And again, this is generic now. What I'm going to talk about on this slide is true generically for bulk viscosity in any context: neutron star mergers, sound waves in air, whatever it might be. What's going on is that some property of the material, in our case it's flavor, the proton fraction, takes a certain amount of time to equilibrate. It doesn't equilibrate instantly. And because there's this little time delay in how quickly this quantity equilibrates, this allows the density and the volume, which go together, of the fluid element to be out of phase with the applied pressure that's giving this oscillation. And the dissipation, the energy loss from the oscillation, is just PDV work done by the oscillation. It's just you compress it, the material, and you uncompress it again, where U is the density oscillation. You are the oscillation. You compress a fluid element and you uncompress it again. And during that cycle, do you do any net work on this fluid element? When you compress it, you do work. When you uncompress it, it does work on you. Does that end up evening out to zero? Or is it more like playing some sort of slot machine, where the more times you do it, the more money you lose? So this is the integral of PDV, and you can write it slightly more in a slightly more convenient way as the integral of pressure times rate of change of volume of the fluid element integrated over one cycle. So it's the integral of P dV dt. That's the energy lost from the oscillation. So in the simple case of something like a Hooke's law spring that just behaves the same way when it's compressed and when it's uncompressed, when the pressure goes up, the volume goes down, or when the pressure goes down, the volume goes up, and it's always on this same line here. And in this case, there's no phase lag and no dissipation. So you can see that in this formulation here, the pressure goes up and the volume, this dashed green line, goes down. They're out of phase with each other. You compress it, it gets smaller. You uncompress it again, it gets bigger. The volume is 180 degrees out of phase with the pressure. dV dt, the rate of change of volume, is 90 degrees out of phase with the volume. Obviously, taking a derivative takes you 90 degrees out of phase. So since dV dt is 90 degrees out of phase with the volume, and the volume is 180 degrees out of phase with the pressure, that means that rate of change of volume is 90 degrees out of phase with the pressure. So this integral is 0. So you're just going back and forth on this line. There's no phase lag. The system is responding instantly to the applied pressure oscillation. But if there's some delay, then you get a situation more like this. In this case, there's a phase lag between the pressure and the density or the volume of the fluid element. So when you increase the pressure and then decrease it again through one cycle, the volume is not 180 degrees out of phase with that. There's a little bit of a phase shift. So the volume is phase shifted. That means dV dt, 90 degrees out of phase with the volume, is not 90 degrees out of phase with the pressure anymore, because the volume isn't 180 degrees out of phase with the pressure. So now dV dt not 90 degrees out of phase with the pressure means this integral is not 0 anymore. What's happening in the pressure volume diagram here is that when you compress it, increasing the pressure and decreasing the volume, it behaves differently from when you uncompress it, decreasing the pressure and increasing the volume. And that's because, thanks to this lag in equilibration time, it takes a little bit of time for the system to catch up. So when it's being compressed, it's remembering that it was recently in a more uncompressed state. And when it's being uncompressed, it's remembering that it was recently in a more compressed state. So it's behaving differently. And that means you can have a little bit of area here in the pressure volume plane, non-zero integral for this PDV integral. And that means the oscillation is doing work in each cycle. And that work is lost from the oscillation. It's converted into something else, maybe heat, maybe neutrinos, depends on the details of the system. So this is what bulk viscosity is. It arises from this phase lag. Now, what you might guess from that feature is that it's in some ways a resonance. In fact, mathematically, it exactly matches onto a resonant RC circuit. And the bulk viscosity is biggest when the internal flavor relaxation rate, the time scale on which protons can turn into neutrons and reestablish the correct proton fraction for whatever density you're at, it's when that flavor relaxation rate matches the frequency of the externally imposed density oscillation. And the bulk viscosity takes this form as a function of the flavor relaxation rate for a given density oscillation frequency. It's got the rate, the flavor relaxation rate, on the top here and on the bottom here. This C in front is just some susceptibilities, some properties of the material. So the bulk viscosity goes like this: relaxation rate gamma over gamma squared plus omega squared. And that means that it's got this sort of shape, the bulk viscosity, if the relaxation rate, the flavor relaxation rate, is very fast. If you've got a system where flavor equilibrates very quickly, that means this gamma goes to infinity, and then gamma is very big on the bottom here, dominates, and sends the bulk viscosity to 0. So if things equilibrate very fast, you don't get any bulk viscosity. And that makes sense just intuitively, right? If it's always in equilibrium, then at every moment as you compress it, it instantly equilibrates. And so it's always at the right proton fraction. And then when you uncompress it again, at each step on the way out, it's got the same proton fraction it had at that density on the way in of compressing it. And so it's symmetric. In and out are just mirror images of each other. So there's no difference between compression and rarefaction. There's no net work done. It's that the work you do is the work you get back. It's all just symmetric. So that's what you expect if equilibration is very fast. And so no bulk viscosity up here at the very fast equilibration end. However, also, if the equilibration is very slow, then you also don't expect any bulk viscosity. So if this gamma relaxation rate goes to 0, then the gamma on the top dominates and the bulk viscosity goes to 0. And that's this part of the bulk viscosity versus relaxation rate plot. If the equilibration is very slow, the system doesn't try to equilibrate. In this case, proton number and neutron number are both conserved. It takes forever to turn a neutron into a proton. So basically, you've got two conserved quantities here, proton number and neutron number. The proton fraction is fixed. So again, at every point on the way in of compressing and on the way out of uncompressing, the system is showing symmetric behavior. The proton fraction just stays constant the whole time. So there's no phase lag, there's no hysteresis, there's no memory. It's just instantly always determined by fixed proton fraction. So again, very slow equilibration means no bulk viscosity. And here you see there's this peak in the middle, and the peak occurs when the flavor relaxation rate matches the frequency of the oscillation. That's when the oscillation is sort of having maximum trouble with the flavor relaxation process, when they're both on the same time scale and they're kind of interfering with each other. So yes, maximum phase lag when there's this resonant agreement between the externally imposed oscillation frequency and this internal property, the flavor relaxation rate. So what we want to know, and what you've already previewed in that plot of the damping time. The damping time is different from the relaxation rate. The damping time is the damping time for sound waves. The relaxation rate is a microscopic quantity which just says what's the time scale on which the proton fraction equilibrates. What merger simulation people need to know is, do we have to worry about flavor relaxation? Does it happen on the millisecond time scale, or is the rate in the kilohertz frequency range? And so you can calculate this. It's implicit. It's already been done in the background of the previous data I showed you about the sound attenuation time. So for the IUF equation of state, you can calculate this relaxation rate, again, in the density temperature plane, and you get a bunch of contours, roughly horizontal contours here, reflecting the fact that it's mainly determined by the temperature. This, I should say, is for, again, we're assuming neutrino transparent matter. Neutrinos are a very troublesome thing in neutron star mergers. And so we're making a crude approximation in this case that the material is transparent to neutrinos. So the processes whose rate contributes to this relaxation are neutron decay into protons and electrons and antineutrinos, and electron capture on protons, turning them into a neutron and a neutrino. So it being neutrino transparent means you have neutrinos in the final state, but no neutrinos in initial states. So these are the two processes that are balancing out to establish flavor equilibrium. And when you look at the rates of these processes calculated using the standard sort of Urca type techniques, you find these relaxation rates in MEV. MEV is not very useful in this case. What's useful to know is what is it in milliseconds, and this green, thick green contour here is when this relaxation rate crosses through 2 pi kilohertz. So that's when the frequency is 1 kilohertz, so the angular frequency omega is 2 pi times 1 kilohertz. That's 10 to the minus 18 MeV. So as you turn the temperature up, this relaxation rate is getting bigger, 10 to the minus 19, 10 to the minus 18, and around temperatures of 4 or 5 MeV, that's where it goes through about 1 kilohertz. So it's sort of amazing in some ways. It so happens that some combination of the weak interaction parameters, the Fermi coupling, if you want to call it that, or the W mass, conspire together along with the amount of phase space available at these and nuclear matter at these densities and temperatures to give you a rate which happens to, at this temperature, match with the astrophysical time scale of milliseconds arising out of neutron star mergers. But so indeed we do hit resonance. You get maximum bulk viscosity when the temperature is in this 4 to 5 MeV range. And so the bulk viscosity will be at a maximum, and that's why we see what we see. So we now see why bulk viscosity is this non-monotonic function of temperature. It's because the relaxation rate is pretty much determined by the temperature. That's because of it's the amount of phase space at the Fermi surface. And so when you vary the temperature, you're pretty much scanning at any given density. If you increase the temperature, you're just ramping up the relaxation rate. You're making it relax faster and faster and faster. And you go from relaxation that's slower than 1 kilohertz to relaxation that's faster than 1 kilohertz. And since 1 kilohertz is the oscillation timescale, is the frequency of the oscillation whose damping we're looking at in this plot here, as you go from temperatures like 1 MeV to temperatures like 10 MeV, you go from a low bulk viscosity because your your proton fraction is equilibrating slower than the frequency of the oscillation, slower than 1 kilohertz, to low bulk viscosity because your proton fraction is equilibrating faster than 1 kilohertz. And when the temperature is about 5 MeV, that's when your flavor relaxation rate through weak interactions happens to match with the 1 kilohertz density oscillation frequency. And as I said, if you assume neutrino transparent matter, this happens at about a temperature of 5 MeV, which is a relevant temperature for neutron star mergers. Does anybody want to ask a question at this point? Don't mind pausing.
I wrote one in the chat. Just this.
Yeah, go ahead.
Yeah, thank you very much. This coincidence, or that the cosmological or astrophysical, not cosmological, astrophysical timescale and timescale from the weak interaction has this exactly at 4 MeV. You have such a nice coincidence. Is it model dependent? So any other assumptions went into this, or just standard model scales?
So it is okay. It's certainly I'm using the standard model here. I'm just doing standard weak interactions. I'll mention later on, just very briefly at the end, possible beyond standard model ideas. But you can look at different equations of state. I'm not sure if here we go. So here is one example of testing this for robustness in the way that maybe you're getting at. I did IUF, and you get these contours. here's a different equation of state, one that's based on matching to chiral perturbation theory in neutron-rich matter. And you get slightly different looking contours. You get a 50 millisecond contour up here at 3 times saturation density. Okay, so you can move it around a bit depending on the equation of state. Okay, the main thing that determines this is actually the behavior of the neutrinos. Is that mine? Here we go. So I think maybe these 2 slides are addressing your question. If they're not, please ask it again. You can also ask about the opposite extreme from neutrino transparent matter, which is matter where the neutrinos are trapped. In every fluid volume, there is a hot gas of neutrinos that's locally equilibrated, just like the protons and the neutrons and the electrons are. So this plot shows you bulk viscosity now in, you know, those crazy units that the astrophysicists love, grams per centimeter per second. But you see the resonant peak as you vary the temperature here in the neutrino transparent regime. They're assuming things are neutrino transparent at lower temperature. And then you can do neutrino trapped at high temperature. And you see that the bulk viscosity is lower in the neutrino trapped phase. And that's for a couple of reasons. One is there's more phase space at the Fermi surfaces, the rates just run faster, and also the susceptibilities are a little bit smaller. So the peak itself, if you track this to its peak would be a bit lower. And in between, and actually even maybe it's optimistic to say we know that it's transparent at low temperature. We know it's trapped at high temperature. Neutrinos are very tough to deal with because their mean free path varies as a function of temperature across just the scale of the size of the system. So it's very difficult to have a correct treatment of neutrinos in this instance. And so probably the correct treatment of neutrinos is the biggest uncertainty in this. And depending on how transparent it is to neutrinos, it might be that you don't really get, if neutrino transparency is a bad assumption and it's not really neutrino transparent anywhere, you might not get this resonance. That's one of the next, and in my next things to do slide coming up soon, that's one of the questions, is how do we go beyond these 2 extreme assumptions of neutrinos just escape versus neutrinos are completely trapped locally? How do we look at the in-between regime? Did I tackle your question?
Thank you very much. Yes.
Okay.
Great detail.
So I think that naturally took me through these next 2 slides. And I see that we're moving on. So I think it's a good time to summarize and give people time to ask anything they want to ask. So the summary is that neutron star mergers are interesting. They probe the dynamical response of high energy matter, unlike heavy ion collisions, which probe it on the 10 to the minus 23 strong interaction time scale. They probe it on this millisecond time scale. But they're both probes of dynamics, just on different timescales. If you assume that nuclear matter is neutrino transparent, then you find that the equilibration of proton fraction of flavor occurs on a comparable timescale to the merger, at least at some temperatures, can't be neglected, should be included in simulations. And you might, the bulk viscosity that follows from that, the phase lag induced by this flavor equilibration happening on the same time scale as the density oscillations, that resonant maximum in the bulk viscosity is strong enough to damp density oscillations, again, on that same time scale. And here's a technical note. There's something about how you calculate the rates. So looking to the future, what should we do? Well, one thing is, obviously, we are in discussions right now with people doing these merger simulations about what is the best way to try to include this physics, which generally they've tended to neglect or only partly include, because it's been hard enough for them, to be fair, just getting an equation of state, an equilibrated equation of state, pretending it's always equilibrated and doing all that nonlinear, dynamically discretized GR is hard enough. So they really only want to add in complications if they have to. So you have to give them some good reasons why they should include additional complications in their work. This next question, though, is an important one that was just touched on. Beyond the 2 extreme assumptions of everything's neutrino transparent versus neutrinos are trapped and form their own fluid, you really want to calculate flavor equilibration rates for arbitrary neutrino distributions. So people could evolve the neutrinos using some sort of dynamical evolution, and that will mean that these weak interaction rates, these flavor equilibration rates, will be different from either of these two extreme cases, and we'd like to see how that pans out. I focused on the most generic vanilla kind of nuclear matter, neutron, proton, electron, but you can also calculate these flavor equilibration rates for other forms of matter. My postdoc Alex Haber has worked on hyperonic matter with hyperons in how quickly it equilibrates. People are interested in other forms of nuclear matter, pion condensed, maybe even nuclear pasta phases, maybe quark matter phases. There's all sorts of things you can look at. So I focused, in talking about the consequences of the finite rate of flavor equilibration, I focused on bulk viscous damping, but there are other possible manifestations of flavor equilibration, like the heating that might go with it or the neutrino emission that it might induce. At the very beginning, I said there are various forms of out of equilibrium physics one could be interested in, so you can look beyond flavor equilibration. You can look at thermal conductivity and shear viscosity, and preliminary estimates indicate these might be significant in the neutrino trapped regime, which we tend to think is at higher temperatures, if there are fine scale gradients on the 100-meter distance scale. And there are indications from the merger simulations. Every time they tighten their grid, they see new structure in the fluid flows at that new scale. So it kind of hasn't converged. So there might well be some interesting physics for small distance scale perturbations if neutrinos are trapped on that scale. And finally, as I just briefly mentioned earlier, you could think beyond the standard model. You could ask what sort of beyond standard model physics might come in and affect some of this out of equilibrium physics in mergers. And I just have one. I keep thinking you keep thinking it's the last slide, and it never is, but this time it really is. My former grad student, now postdoc at INT, Stephen Harris, collaborated with these experts on axions and looked at cooling by axion emission in hot matter, the kind of matter you might get in a merger, these sort of temperatures, which mergers do reach if you believe the simulations. So this is as a function of an axion-like particles coupling, and as a function of the temperature, what's the time for a hot region to cool off to half its original temperature? And he's got these contours here, 1 millisecond, 10 milliseconds. And what you see is that if you believe the constraint from Supernova 1987A, which says the coupling needs to be below this value, it's still possible that at the very hottest temperatures, axion emission could cool a blob of hot matter on this 10 millisecond timescale, which is, as we've seen, the relevant timescale for a merger. So this is just one example of how people have thought about neutron star mergers as not only a probe of the properties of dense matter, but also possibly a probe of beyond standard model physics. So that really is the end. Thank you.
Well, thank you so much. Are there any questions for Mark? So while folks are thinking, there's something that I never fully appreciated until it suddenly struck me during a talk a couple of years ago, which is that, so these folks are doing non-dissipative simulations, and they start with 2 neutron stars that are cold, 0 temperature on the way in. And indeed, since there's no dissipation, they cannot be heated by tidal forces or anything. They're still at 0 temperature when they collide. And then their only heating mechanism is really shock heating, because it's completely ideal fluid dynamics. And that may well be right, but I'm actually not totally sure how sure they are that this is right, that it's all shock heated. Have you ever thought about this?
So no, I mean, I'm roughly at the same stage you are, which is you talk to them and you ask them, where does the heat come from? Where does the entropy come from? And they say shock heating. And then you think, is that really all? And so part of what we're doing here is looking at another possible source of heat, but it's not the only one. And yeah, it does make you think, are there other heating mechanisms that they're neglecting that could be significant contributors to the entropy? But yeah, basically the entropy is just flowing along with the fluid, along with the baryon number in the way they're doing it now. And it's not clear that that's right. In fact, the neutrinos, you know, it's emitting neutrinos. Well, it depends what temperature. Again, it goes back to the neutrinos are always the stumbling block. And so the neutrinos are presumably taking away energy. They're presumably taking away entropy. There's thermal neutrino radiation, and I'm actually not clear if that's, you know, they're taking that into account.
Is it being heated by nuclear reactions at some point? Not really, not early on.
I don't think so, no.
I mean, at late time, there's some heating from radioactivity.
Yes, in the outer, in the very outer parts. I'm more focused, obviously,
Right.
as you saw, on the sort of saturation density and above range.
We have a question by Misha. Do you want to unmute yourself?
Yes, hi, can you hear me?
Yep.
Yes.
Yeah, thanks. It was an interesting talk. I just wondering, following your description of bulk viscosity, that it's maximized in the regime which is on the boundary between the one where proton fraction completely equilibrates and the one where it's frozen. I was wondering if the difference in equation of state is also taken into account in between these two regimes. If proton fraction is frozen, then the equation of state is stiffer, and the sound velocity is faster. Right. So if you want to consider a regime where this resonance occurs, then you obviously straddle these two regimes, and so equation of state has to basically capture both of these two limits. Is that something which is taken into account? If it isn't, do you think it could lead to some effects?
Okay, so remember that, so the calculation that I presented is in the linear response regime, so it's very teeny-weeny density oscillations. So I think in some way the dissipation is arising from the system sort of trying to transition between those two equations of state. It's PDV work, right? So it's coming from that attempt of the system to get the right equation of state. So I think that the bulk viscosity basically is the consequence of this catching up attempt to go between those two equations of state that you're describing. Now, if you were looking at large amplitude oscillations, then you'd really be, okay, then it's not linear response anymore. Then it may start depending on the amplitude of the oscillation. Then it's less trivial. It's the suprathermal regime. But I think if I understand what you're talking about, that is what we're trying to capture here.
Yes, I just want also to point out that this coefficient C, which you said depends on, is actually proportional to the difference between the square of the speed of sounds in these two regimes. So, so the amplitude of your resonance is actually proportional to the difference between these two equations of state. So if these two equations of state are almost identical, then there will be no bulk viscosity, no resonance at all. So it is important.
Right. If there's, but what you're saying is,
it's another way of saying what you said.
Yeah, if the proton fraction didn't want to vary as a function of density, there'd be nothing going on. I'm just going to.
That's not what I'm saying. I think what I'm saying is that even if the proton density were to vary, but the pressure would not depend on it. Suppose that pressure would be completely impervious to the, which it isn't, but suppose it was. Then whether the proton fraction is frozen or not, the speed of sound will be the same. Then there will be no bulk viscosity.
Right, I agree. You can get a situation. Let me go back to where I want. Oh, wait a minute, I overshot. Okay, this don't know. here we go. Yes, you can get a situation, you're right, you can get a situation where this coefficient in front is 0. Right, that can happen. Where as you say, there's no difference in behavior between the it's what you said. So
yes,
that can happen. True. I'm not sure what to say other than yes, that can happen.
Yeah, so what I wanted to say is that if the during the merger or any other process where this kind of phenomenon is important, it means that the system presumably spends some time or some spatial regions are in different phases or in different regions of the where the equation of state is either frozen proton fraction or completely equilibrated proton fraction, which means that if one naively does the simulation with a completely equilibrated proton fraction, one would not only underestimate the dissipation, but also will underestimate, let's say, the frequency of the sound oscillations.
Right, that's right.
So right.
So what they have, so people haven't really included flavor equilibration in a full way, but they have done the two extreme cases you're describing. They've done frozen proton fraction and instantly equilibrated proton fraction, and those lead to somewhat different outcomes. Not hugely different, but as you say, the equations of state are a little different, so they're a bit different.
But shouldn't the correct approach involve flexible, so to speak, equation of state, where the proton fraction equilibrates on the same scale as the expansion itself?
Right. So what we're talking to the merger simulation people about is including this flavor relaxation in their dynamics. So they would evolve the proton fraction dynamically. They wouldn't include bulk viscosity in their simulation. They would include the microscopic physics that would naturally lead to bulk viscosities. They include the equilibration in each fluid element as part of its evolution time step. It does the weak interactions and evolves its proton fraction, as well as evolving its volume and all that stuff.
I think it's something which I would call Hydro Plus, where you have dynamic degree of freedom and the degree of freedom which relaxes locally, but on a time scale comparable to the relevant, right? Okay.
Yes, that is from my understanding of what Hydro Plus is. This is Hydro Plus.
Yeah. That coincides with what I think about it too.
Yeah, or just multi-fluid hydrodynamics. I mean, you decide how many fluids there actually are.
Yeah, but you also take into account the processes which violate conservation of all the of all those numbers at a finite time scale.
So this IUF equation of state, what does that actually stand for? What is that?
Oh God, I don't know. I think it might be the is it the institutions that is it Indiana? Somebody, maybe Florida, I forget. Ooh. Yikes, we don't want that.
So some kind of relativistic mean field thing, or?
Yes, it's a relativistic mean field theory.
I see. Yeah, that too is a tricky regime, isn't it? I mean, I guess 5 MeV one should in principle do by kind of chiral perturbation theory, but once you get to higher temperatures, that's probably again a tricky regime to construct reliable equations.
Well, so that QMC equation of state that we used is one that we cooked up ourselves by matching to chiral perturbation theory for neutron matter at low temperature, and then you just use the relativistic mean field theory to do the extrapolation to high density and high temperature. So you're relying on that description, that model of nuclear matter for that purpose. So since people are doing chiral perturbation theory at higher temperatures now, we're interested in seeing if relativistic mean field theories can reproduce what they get. And we like relativistic mean field theories because in order to do these weak interaction calculations, you need the dispersion relation of the neutrons and protons. You need to know what's the phase space like for those Urca processes. So you need that microscopic information you need a field theory, basically. You can't just be given an equation of state. You need to know what the microscopic degrees of freedom are like.
I see Yin has a question.